So good morning student. Today I am going to discuss a very simple subject of chemistry, that is acidity function. The undergraduate student may not be aware of this acidity function, but most of the postgraduate students do know about this acidity function. Now if I am talking about the pH, every student is well versed about the pH. pH scale is open-ended. If I ask a very simple question that what is the pH of hydrochloric acid solution whose concentration is suppose 1 into 10 to the power minus 3 molar or 1 is to 10 to the power minus 4 molar, students can easily reply because it is a simple translation. But if I ask what is the pH of a concentrated hydrochloric acid solution whose molarity is 10 molar, 10, or what is the concentration of a 10 molar sodium hydroxide, then it will be very difficult for a student to reply my question. Like we have three solutions, 1 into 10 to the power minus 3 molar hydrochloric acid solutions. Second is 10 molar hydrochloric acid solution. And third is the 10 molar sodium hydroxide. My question is that what is the pH? So it is simply translation, because you all know that pH is equal to minus logarithm of activity of hydrogen, or you can call it as a pH is equal to minus log of hydrogen and concentration. So it is 3. Okay. But if I just want to calculate the 10 molar hydrochloric acid solution with the same formula, so log of minus log of 10 or log of 10, that is equal to 1, so it is minus 1. So is it possible, because we know the pH range is 1 to 7 and 7 to 14. These are all very common things. So how we explain these things? Second, same thing, minus log of OH is equal to minus 1 and pH plus pOH, you all know, is equal to 14. So here pH is equal to 15. So again there is a big question mark. That means we all know that how do we explain this very unusual behavior. Generally what happened, the pH less than 1.5 and greater than 13, so it indicates that this particular concentration what we are thinking about the pH, it would be much stronger than it would suggest. So therefore, a great scientist, his name is L.P. Hammett, who discovered this concept of non-ideal acid or base solutions, which is called the non-ideal. That means this Sorenson pH scale is not applicable for non-dilute acid region or non-dilute basic solution. So therefore, a new concept should be required, and that is called acidity function. Today, I will discuss acidity function. Is a very big concept. There are certain applications, but in the first part, I will only discuss some of the fundamental of acidity function and how we can define the acidity function, and this unsolved question can be replied with the help of this acidity function. Because generally in undergraduate classes, student can also solve in any competitive examination like a very dilute solution, 10 to the power minus 7 m or 1 into 10 to the power minus 8. It is a very, very dilute solution. And if I ask you what is the pH, again there is a problem, it should be 7. But when we solve this equation, we have seen that the pH is maybe approximately 6.5 or 6.7 or 6.9. We will calculate that. Why? Because here again is the role of hydrogen ion. If the solution is very dilute, the concentration of the hydrogen ion produced by the dissociation of water and the concentration of the dilute acid is suppose 1 into 10 to the minus 7. So we have to calculate the exact concentration of the hydrogen ion. So the whole story regarding the hydrogen ion. Even if you want to solve this very simple question, so sometimes we need some very little bit mathematics, that is called the quadratic equation. So in quadratic equation, we can solve the actual concentration of hydrogen ion. And if we know the actual concentration of hydrogen ion, the pH can be solved. So let me explain the acidity function, and I must tell you some of the, because acidity function is a research oriented topic, but fortunately there are many good books are available. So if you want to study more about the acidity function, you should refer some of the good books and some of the research papers, because I have collected most of the information from those good books and some of the research paper written by L.P. Hammett. Basically, actually I should say that he is the founder of physical organic chemistry, and he was a professor of Columbia University, USA. So before I going into details of the acidity function, as I have already mentioned that there are many good books available, and because most important thing is the role of the proton. So you must read this very, very famous book, Proton in Chemistry. by R.P. Bell, a very well-known scientist, and a book written by the Professor L.P. Hammett, that is called the Physical Organic Chemistry. In addition to that, there is a book of Rochester, I think, yes, this a complete book on the acidity function, that is called the C.H. Rochester, and in addition to that, there are some monographs available in our library. I am talking about the Pandit Ravi Shankar Shukla University library. When I was a student working with Professor S.G. Tandon for some very simple hydrolysis reaction, long back, I think in 1980 or 81, then we have purchased this Advances in Physical Organic Chemistry and Progress in Physical Organic Chemistry. And this book is very common for the M.Sc students. There is a one part where you can get the information of the acidity function as well as the application of the acidity function. It is a course in our university. Then similarly, this book is also very important. This book is also available in our library. The Proton, the Application to Organic Chemistry, the Ross Stewart is another very well-known physical organic chemistry. And you can refer this physical organic chemistry, Isaac Neil book. So these are some. And then if you want to learn more about the acidity function, so you should refer the paper published by this great scientist, I should say, he is Professor L.P. Hammett. So therefore, the first acidity function when developed, this is called the Hammett acidity function. And if you ask me that what is the actual definition of the, when I will explain, then you can understand it is very related to the pH. It is very related to the pH. Sometimes we can call it the extension of the pH. Sometimes it is called it is a measurement of the strength of an acid. So, and he has written so many papers. In 1932, actually first L.P. Hammett and A.G. Dayrup, they actually published the first paper on the acidity function. So therefore, we can call Hammett acidity function. After that, there are large number of acidity function developed, acidity function for amide, acidity function for alcohol, acidity function for indoles. These are of course all research oriented topic, but for M.Sc students, they must know the simple derivation of the acidity function and application of acidity function in chemistry, particularly the determination of protonation constant, determination of the reaction mechanism, and of course it is for, always remember that this acidity function will be useful for reaction mechanism in very concentrated acid solution. I think whenever we discuss about the acidity function, we must salute the another great scientist who discovered the pH actually. Long back in 1909, Sorensen, S. Sorensen, a Danish chemist, he actually introduced the concept of the pH. And acidity function is the extension of this pH. So therefore, we must consider the contribution of this great scientist, Sorensen. And then of course, nowadays after acidity function, there is another concept that is developed by the Cox and Yates, that is called the excess acidity. I will not discuss the excess acidity, I will only discuss the acidity function. Now, my today's agenda is that I will discuss the first Hammett acidity function, and then of course I will also discuss another example, that is called the acidity function for the alcohol. Basically, when he studied the acidity function, that Hammett has taken large number of primary amines, and then he used different acids like hydrochloric acid, sulfuric acid, and perchloric acid. And for alcohol acidity function, they have taken some alcoholic compounds and add some acid. Similarly, acidity function for basic solutions are also available. Acidity function for the basic solution. Acidity function for hydrofluoric acid is also available. Acidity function for superacid is also available. But I will concentrate only on the hamate acidity function and alcohol acidity function, and maybe the acidity function for alkaline solutions. Now, another very famous scientist, his name is John Sauter, and he also visited our country and delivered several lectures when we celebrated the centenary of birth of Louis Hamate. He is also a physical organic chemist, and there is a very good book, John Sauter, by correlation analysis. So, the student can refer this review article regarding this Hamate equation. Now, this is the original research paper of the Hamate. So, you have seen that the name of that paper is the theory of the acidity. That is the most important part, how we measure the acid strength of a very concentrated acid solution. And this is the paper, as I have already mentioned, that in 1932, you have seen that Hamate and his student A.J. Dairup in Columbia University, then and this paper is the landmark of the acidity function. So therefore, we must always refer this very historical paper, and that is the tendency of the acid, or you can call it is a measurement, how you measure the strength of sulfuric acid or perchloric acid, and you will be surprised to know that if you ask me what is the acidity function of sulfuric acid, 100% sulfuric acid, it may be minus 12 like that. And even for, you all know regarding the superacids, their acidity function is maybe minus 28. Can you imagine? The acidity function is minus 28. And nowadays acidity function for deuterated acid is also available. That means for D2SO4, for DCl and other things. After the discovery of Hamate equation, many scientists in the world, they have done a lot of work, and one of the group of University of Toronto, Canada, because I always mention the name of these two scientists, Professor Keith Yates and his student R.A. Cox. They published a review article, and in this review article there are 337 references. They have given 337 references, and if I am not wrong, they have discussed almost around 50 acidity functions in different media, because you all know that the strength of the acid is sometimes depends upon the medium. So you can also refer this, one of the very important review article on the acidity function, that is published in, I think, Canadian Journal of Chemistry long back 1983. And they has given every information about this acidity function. And in our country also, many physical organic chemists, as I have already mentioned, that my teacher, Professor S.G. Tandon, is one of the leading physical chemistry of our country, and he has also done a lot of work on this acidity function in non-dilute acid region. He has done large number of chemical reaction in the sulfuric acid, perchloric acid, hydrochloric acid, as well as the D2SO4. And one great scientist, Professor Chetty Kalidas, he was from IIT Chennai, IIT Madras. He also visited this chemistry department, Ravi Shankar Shukla University, and he has also, sometimes what happens, suppose you want to determine the acidity function of a compound which is not soluble in water. Then what happens? Suppose you need some protic or dipolar aprotic solvent. So the acidity function is also depends on the solvent. So this Chetty Kalidas, he actually derived or determined the acidity function in some solvent also. These are all research oriented topics. I am coming to the student point. Then you all know that always we refer as a teacher most of the good journals of the American Chemical Society or the JACS, and you see that, but there are certain limitations. As I have already told you, that the limitation of pH is the development of the acidity function. The limitation of the acidity function, the development of the excess acidity or excess basicity. So there is also some limitations, and that is also breakdown of the Hammett acidity function concept. I will not discuss all this negative point of the acidity function or the limitation of the acidity function. Rather, I will discuss the very simple derivation of the acidity function. Let me, now I am coming to the simple definition for acidity function. You all know, as I have already given you some hints, that if the solution is very dilute, so whatever the concentration, there is no problem about the activity coefficient, because activity coefficient remains 1. So therefore it is a simple translation. But when we increase the concentration of this acid, non-dilute or strong acid, then of course this is your old equation, Henderson-Hasselbalch equation, or whatever the activity coefficient concept must be considered. I will come to that point. So Hammett acidity function is a measure of acidity. It is a scale, and for one of the most important application of acidity function is that the figure out of acid catalyzed reactions. Again, it is for the general knowledge question that nowadays we are talking about the superacids, and you will be surprised to know that some superacids, like a mixture of hydrochloric acid with antimony pentafluoride, is 10 to the power 16 times stronger than sulfuric acid. So how do you use the pH? It is impossible. For superacid, a great scientist, you know, George Olah, who is a Nobel laureate, he also determined with the concept of acidity function for the such type of superacid like minus 28 or like that. As I told you that sulfuric acid is minus 12 and other things. This is the Hammett acidity function for some superacid systems. Very fast, very strong acid. Now I am coming to the derivation part. Now you see that there are three terminology. Now this is for Hammett acidity function, this is for amide acidity function, and this is for acidity function for basic solution. We will not call that basicity function. If we are using the basic solution, we will call acidity function for basic solution. Now I am coming to derivation part. Very simple derivation part. I have already discussed these things. Now again it is very simple question. Again it is for the undergraduate student, that if the solution is very dilute, even 1 into 10 to the power minus 8. So you have to calculate actual hydrogen ion concentration, because the hydrogen ion contributed from the this solution cannot be ignored because it is very close to concentration of water, because we know that the ionic product of water is 10 to the power minus 40. So simply you can also calculate that total concentration of hydrogen ion from the water dissociation and total concentration of hydrogen ion from that acid solution. But if you want to really calculate the actual concentration of that hydrogen ion, so you all know this thing, quadratic equation, so we can solve all these things. I will not discuss this quadratic equation. Similarly, for this you can also solve like that, because concentration of water is 10 to the power minus 7, concentration of acid is 10 to the power minus 8. We can write it 0.1 into 10 to the power minus 7. So actual concentration is 1 plus 0.1. So total is, so that is also one simple solution, and then by simple translation. So you see it is not minus 8, but it is 6.9. Now I am coming to the concentrated part. Now before going into details, I must tell the student, that is also another concept, that if the solution is very dilute, the concentration, or sometimes it is called the stoichiometric concentration, and activity coefficient is same. But if the solution is non-dilute, so we have to consider the activity coefficient. So now I am just, last part is the derivation of acidity function. Very simple. Derivation of acidity function. First is H0. H is Hammett. So first thing is that he has taken some bases, primary amines, large number of, add acid. Acid may be hydrochloric, may be sulfuric, may be perchloric, may be deuterated, may be D2SO4. If it is deuterated, so you can call it D0. Anyway, so it is protonation, you all know, it is B plus H. Now if it is other type of compound, so in place of aniline, you can take the amide. If it is indole, we can take some indole compound. If it is alcohol, so we can take alcohol. If it is hydroxamic acid, you can take hydroxamic acid. So acidity function will measure the strength of how it protonates. So very simple derivation, that here I can write like that, B plus, so B plus H. Very simple. So K, equilibrium constant, or sometimes it is called the protonation constant, is equal to bear in mind it is a non-dilute or concentrated. That is the most important point. So, it is, activity of B, activity of HI, and activity of BH plus. Okay. Now, if it is dilute 1 molar or less than 1 molar solution, then of course activity is equal to concentration. But as I told you, that is a non-dilute solution, so I have to consider multiplied by a activity coefficient terms. So this is activity is equal to stoichiometric concentration, or sometimes you can call molar concentration, and that term is called activity coefficient. So I can write like that, KBH is equal to, now this activity of B is equal to whatever the concentration, molar concentration of B and activity coefficient of B, then activity of hydrogen divided by, again, molar concentration of the protonated species, because you take the aniline, primary amines, add any acid, it gets protonated, so it is a protonated species. And then again activity coefficient of BH plus. Taking logarithm, very simple derivation. So taking logarithm, log of KBH, I am just doing nothing, no integration, no differentiation, very simple, only logarithm is equal to log of B divided by BH plus call it, then plus, we can write like that, AH F of B, activity coefficient, F of BH plus. If I do whole equation minus, see here, so just I convert it. So it is minus log of KBH is equal to minus log of B divided by BH minus activity of hydrogen, activity of B, activity of BH. You just see this red color. So we all know that minus log of kBH is sometimes it is called the pKBH. pKBH. And if I write just plus, so log of BH plus, I just change the sign, B, and this minus this term. Now now imagine, if the solution is very dilute, if the solution is very dilute, there is no difference between this molecular species and protonated species. So this part can be avoided. If the solution is very dilute, I am talking about the solution is very dilute. BH, that means your acid is unable to protonate this base. So this part can be eliminated. So what happened? And solution is dilute, so there is no question of activity coefficient of molecular species and activity coefficient of protonated species also we can remove. So it will get only minus, oh sorry, we should write here, just you correct it, you should. Is also log, if I write here, so log, right, log of minus plus log of activity of, sorry, log. Again, I should write again. So I'm just sorry. So pKBH log of BH plus B minus log of activity of hydrogen. Here is also log F of B, F of BH plus. That's all. Again, I am saying same thing. If the solution is very dilute, so this part is, if the solution is very dilute, so this part can also be, if the solution is very dilute. If the solution is very dilute, no question of activity and activity coefficient. So what is this? Minus log of H is equal to, this is the pH. But for non-dilute region, we cannot ignore the activity coefficient. So final acidity function is equal to pKBH is equal to log of BH plus and B. Sometimes this is called actually ionization ratio. Ionization ratio minus log of activity of hydrogen, F of B, F of BH. Now this right hand side whole part is called acidity function. So therefore H0 final definition is minus log of activity of hydrogen, activity of P, activity of BH plus. So this is the acidity function. And then depending upon if it is a hydrochloric acid solution, the value will be changed. If it is sulfuric acid solution, value will be changed. If it is perchloric acid solution, the value will be changed. So I can give another example so that the students can understand very easily. It is for Hammett acidity function. This is Hammett acidity function. This is called the ionization ratio. So if you understand this solution, you can also determine the protonation constant of any unknown bases with the help, but you must know the value of acidity function. So my last part is that I will solve one more, that is called the alcoholic acidity function. That's the last part. Last part is that if I take one alcohol, so that you can understand. Suppose this is ROH. Sorry. Now it is for acidity function for alcohol. Any type of alcohol. Any type of alcohol. Plus. So we add acid. So H2. So KROH. Again it is for non-dilute acid region. Take alcohol, add some acid. So it is activity of R plus, same concept. Activity of water, activity of ROH, activity of hydrogen ion. As because it is non-dilute acid region, so as I have already told you that activity is equal to concentration into activity coefficient. Concentration and activity coefficient. So I can write like that. R activity coefficient of R, activity of water, concentration of alcohol, activity coefficient of, and of course activity of hydrogen ion. Same thing, taking logarithm. So log of KROH is equal to, same thing, log of R plus ROH plus log of FR, activity of water, FROH, and activity of hydrogen. See this side. So again, if I take minus, 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 you know, minus log of K, Pk is equal to minus log of K. You all know the very simple formula. So it is PKROH, alcohol, is equal to minus log of R plus divided by ROH or minus we can call it minus and just so minus log of F of R activity of water, F of ROH activity of hydrogen. So just like same thing, this part we can call it is HR acidity function, or like just we rearrange it. That means so pK ROH minus, if we call it plus log of R plus and ROH is equal to this part. This is actually alcoholic. If I do it plus, so like that log of activity of hydrogen F of ROH divided by F of R and activity of water. So by that simple method, any acidity function can be determined. I'm just giving one or two examples, that's all. So the last part is that today I will not discuss about the application part. Now, as I have already tell you this methodology, and again same thing, that log of, sometimes it is called this log of activity of hydrogen, activity of B, and this is, and similarly this is the activity coefficient of for this system, and we can change it like that if I do it like that. These are the some values of acidity function I have taken from this book. For any type of hydrochloric acid, nitric acid, hydrofluoric acid, these are some values of acidity function. Suppose these are your sulfuric acid is suppose 10%. Sulfuric acid is 10%. So the acidity function, you know that, because generally pH value is 1 to 7, 7 to 14. But here you are able to measure less than 1. That means minus 1, minus 2, minus 3, like minus 4, minus 5. Concentrate is minus 12. So these are the just like pH scale 1 to 7. Here it is, suppose it is 20%. Sulfuric acid is 20%. pH is, the acidity function is minus 1. Then if it is 30%, you see minus 1.6. 40% minus 2.35, like that. So again 50%, 60%, 70%, maybe minus 10. So this is the acidity function scale I have taken from a research paper, Canadian Journal of Chemistry. Similarly for DCl and D2SO4, as I have already told you that it is also available for deuterated solvent, like that. Now you see acidity function values, because the protonating capacity of different acids are different. Hydrochloric acid may be very strong, perchloric acid may be very strong. So you see that suppose 10 molar hydrochloric acid, the acidity function is minus 3.68, but for perchloric acid is minus 7.9, it is 4.9. Similarly for alkaline solution, because again alkaline solution is 7 to 14. So beyond the 14, as I told you, if the sodium hydroxide is 10, so that pH is equal to like that. This is negative acidity function, that acidity function for alkaline solution by Rochester. There are many applications, but today I will not discuss the different types of the applications. But basically, first is the determination of the protonation constant, and second is the determination of different types of acid catalyzed reactions. Suppose the total number of water molecules involved in the rate determining steps, the role of water as a proton transfer agent or hydrogen donor, or there is no role of water like unimolecular reaction, water is not involved. But suppose it is a bimolecular reaction, then how many water molecules are involved? 2 or 3. That can be solved with the help of the acidity function. There are different names like Zucker-Hammett hypothesis, Burnett-Olsen parameters, Yates-McClellan parameters. I will not discuss today. I will just only discuss the simple acidity function, and these are the very simple example of protonation constant determination. That means if you take any type of base and gradually adding sulfuric acid or hydrochloric acid and monitor their absorbance, because when you change the concentration of sulfuric acid, your protonated species may be changed. And H0 value, so if you plot a graph between H0 values and log of ionization, this is called the ionization ratio. So there must be a straight line. So from that slope value, you can, if you write y is equal to mx plus c, so you can determine the pKbH value. So that is the application of acidity function. In second part of the acidity function, I may try to discuss the application of acidity function. Thank you very much.